Welcome back to the Master AI series. In our first episode, we really zeroed in on one core principle, that all AI learning is basically a process of optimization. But, that simple rule doesn't explain the incredible diversity we see in AI today.
So, last time, we established that, at its heart, learning is about minimizing error. An AI tries something, it measures how wrong it was, and then it tweaks itself to be a little less wrong next time. It's a universal concept that applies to every single AI out there.
Okay, but that leaves us with a huge question, right? If the learning process itself is universal, why are AIs so different? Why is the brain inside a self-driving car, which has to be an expert at seeing the road, so fundamentally different from the one in a language translator, which has to master the sequence and flow of time?
This is episode 2 of the Master AI series, and today we're going to explore a simple but incredibly powerful idea, that for an AI, architecture is destiny. The very structure of its network is what determines what it can see, what it can remember, and ultimately what it can imagine.
We'll kick things off with the foundational network that started it all. Then we'll dive into architectures built to see in space, others built to remember through time, and some designed to compress information down to its absolute essence. And finally, we'll wrap up with a couple of really specialized designs.
All right, so to really get a handle on these specialized brains, we first need a baseline, a sort of default setting. And that starting point is the multi-layer perceptron.
In an MLP, the rule is total connection. Every single neuron in one layer is connected to every single neuron in the next one. It's a global free-for-all of information. Now, this is really powerful, but it makes one huge assumption. It assumes that every piece of input data is equally related to every other piece. And as we're about to see, that's almost never the case.
Now, when you stack a bunch of these layers on top of each other, you get what's called a deep neural network, or DNN. And that depth is key. It lets the network build up ideas in a hierarchy. Simple patterns in early layers get combined into more and more complex concepts in deeper layers. But what happens when that mix-everything approach is actually a terrible idea? That's where this design starts to show its cracks.
Which brings us right to our first specialization. I mean, what if your data isn't just a flat list of numbers? What if it's an image where the pixels right next to each other are way more important than the pixels on opposite corners of the screen?
This is the exact problem the convolutional neural network, or CNN, was built to solve. Instead of connecting everything to everything, a CNN uses this small, sliding window called a filter or a kernel. You can think of it like a little pattern detector that scans across the image looking for just one specific thing, like a vertical edge, or a curve, or a patch of color.
And this is where you really see the genius of it. An MLP is global chaos. A CNN is smart, it's local. It has a built-in assumption, a bias, that things that are close together in space probably belong together. This makes it incredibly efficient for anything that looks like a grid. The network doesn't have to waste time learning that the pixels forming an eye are near each other. Its structure already forces it to look for those local patterns first.
And just like with DNNs, when you add depth, you get a hierarchy. The first layers of a CNN learn to spot really simple things: lines, edges, colors. The next layers combine those into textures and simple shapes. And the layers deeper still assemble those shapes into complex objects, like faces, cars, or buildings. The architecture itself is fundamentally biased to see the world.
Okay, so that's space covered. But what about data, where the most important relationship isn't spatial position, but sequence? I'm talking about words in a sentence, notes in a song, or stock prices over a month. Here, the order is everything.
For this, you need a totally different kind of brain, the recurrent neural network, or RNN. The defining feature, the thing that makes an RNN an RNN, is its feedback loop. As it processes one item in a sequence, let's say the first word of a sentence, it produces an output, but then it also loops a piece of that information back into itself. That becomes part of the input for the very next word, creating this chain of context, a sort of memory that it carries forward through time. But this simple form of memory has a massive, catastrophic flaw. It's called the vanishing gradient problem. It's kind of like a game of telephone. The influence of what happened at the beginning of a sequence just fades with every single step. By the time you get to the end of a long paragraph, the network has pretty much forgotten how the whole thing started. The learning signal just fizzles out.
So to fix this, we needed a much more sophisticated kind of memory. And that is exactly what architectures like the Long Short-Term Memory Network, or LSTM, provide. LSTMs have these clever internal mechanisms called gates. You can think of them as little control valves that actually learn how to manage the flow of information. They learn what's important enough to keep, what they can safely forget, and what to pass on. Their whole architecture is biased to remember what matters over long stretches of time.
So we have networks that can see in space and networks that can remember through time. But what if our goal is something else entirely? What if we want a network to just understand the essence of something by learning how to compress it?
This is the job of the autoencoder. It's a two-part system. First, an encoder takes something rich and complex, like a big image, and squishes it down through a tiny bottleneck into a super-compressed, low-dimensional code. Then, the second part, the decoder, has to try and reconstruct the original image using only that tiny bit of compressed information. To have any chance of succeeding, the network is forced to get incredibly good at figuring out what information is absolutely essential and what's just noise it can throw away.
A standard autoencoder learns one single precise code for each input. Think of it like a library call number, one specific book. But a variational autoencoder, or VAE, learns something way more flexible. Instead of a single point, it learns a range of possibilities, a sort of probability cloud. This creates a smooth, continuous map of concepts, which lets us not just reconstruct things, but actually generate brand new ones by exploring the space between the concepts it already knows.
Okay, finally, let's look at two architectures that take these core ideas to the absolute extreme. These are networks designed for incredibly specific tasks, one for perfect reconstruction and the other for pure generation.
First up, the U-net. It has that same encoder-decoder structure, where it compresses information down and then builds it back up. But its killer innovation is something called skip connections. These are like direct pipelines that copy high-resolution details from the earlier layers of the encoder straight over to the late layers of the decoder. This means the network doesn't lose all those fine-grained details during the compression process. And that's exactly why it's so brilliant for things like medical image segmentation, where every single pixel counts.
And then there's the generative adversarial network, the GAN. This isn't one network, it's two, and they're locked in a constant game. You have the generator, which is basically an art forger, trying its best to create fakes that are completely indistinguishable from reality. And you have the discriminator, which is like an art detective, whose only job is to get better and better at spotting the fakes. They train against each other in direct opposition. As the forger gets better, the detective has to get smarter. The result of this endless arms race? A generator that can create astoundingly realistic and totally novel content.
And this really brings us full circle, back to our central theme. From that simple, fully connected network to this complex adversarial game, the structure we choose isn't just the box we put the learning algorithm in, it is the filter through which the AI experiences and interacts with the world.
So let's just summarize it one last time. The MLP is the generalist. It mixes everything together. The CNN is the visual specialist, biased to see patterns in space. The RNN is the temporal specialist, biased to understand sequence and memory. Autoencoders are built to find and compress the essence of data. And GANs, well, GANs are designed to imagine entirely new realities. Each architecture is a purpose-built brain for a purpose-built task.
This was episode 2 of the Master AI series. We've seen all of these different specialized brains for seeing, for remembering, for imagining. But it begs the question, what if you didn't need them all? Could a single, powerful architecture do it all? In our next explainer, we'll examine the breakthrough that attempted to answer that very question, the transformer.